This video lecture is meant to teach you about the periodic table, specifically the patterns or the trends that are in the periodic table. Sometimes this is referred to as periodicity, the trends and the patterns that emerges. The objective that we will be covering in the context of this lecture is from your objective sheet. It says to describe and give reasons for trends among the elements in regards to atomic size. And when we say atomic size, I am referring to both atomic mass and atomic radius. So how heavy and how much space they occupy. So within this periodicity chapter, which is from section 3 of chapter 6, we're going to be studying these properties of the elements to see, and we're going to analyze how they change in two directions. First, within a period, going left to right horizontally, or within a group as we go top down within a vertical column. There's 4 properties that we're going to be taking a closer look at. First is atomic mass, how heavy these atoms are. Then atomic radius. And in a later lecture, we'll be looking at both metal reactivity and non-metal reactivity. So atomic mass is defined as the weighted average mass of all of the atoms of the element. If you remember, all of the atoms refers to all the isotopes of that element. Okay, so how heavy these atoms are. If you were to take a look at this periodic table, you can see, if you were to look in a vertical column, if we take a look here, beryllium weighs about 9 atomic mass units, magnesium weighs 24, calcium's 40, strontium's 87, and so on and so forth. You can see that as you go down in this column, and if we were to do it on any of these columns, carbon, silicon, germanium, tin, and lead, as you go down a column, the mass gets heavier. What happens as you go left to right? Okay. Potassium's 39, calcium's 40, scandium 44. Moving across, we see here that the mass increases with occasional hiccups here. Occasionally is not always a perfect trend, and it's not an even trend, but as you go across from left to right, there is an increase in the mass of the elements. So summarizing this, top to bottom within a group, there is an increase in mass. Why? Why does the mass increase? Well, top to bottom, what gives an atom its weight? Well, protons and neutrons. And as you go top to bottom within a column, you're adding lots more protons and lots more neutrons. Left to right within a period, there is also an increase in the mass, really for the same reason. As you go left to right within a period, you're adding 1 more proton and usually about 1 more neutron, but it varies. Okay, so 1 more proton and 1 more neutron is the reason for these atoms getting heavier. So if you were to summarize or try to visualize the atomic mass trend, that if we were to draw an arrow here, the atomic mass increases as you go down the periodic table, and the atomic mass increases as you go to the right of the periodic table. So the heaviest elements end up over here in the bottom right hand corner of the periodic table, and the lightest elements end up in the upper left corner. As a general trend, there are always some exceptions to the rule. The next trend we're going to look at is atomic radius, which is defined as the size of the atom, which can be measured in several different ways, but typically the radius is measured when you have 2 atoms bonded together, and scientists are able to determine the distance between the nuclei of the 2 atoms, and if you take that in half, of course, then you have the radius of the atom. So radius is, of course, a measure of how much space the atom actually occupies. So you've created a graph, actually 4 graphs, on your graph paper. And what I'd like you to look at first is within a group. Specifically, you'll be looking at the alkali metals and the noble gas graphs. So top to bottom, within a group, what you should notice is that there is an increase in the radius. The atoms get bigger as you go down that column. But when you go left to right within a period, this would be period 2 and period 3, you'll notice something very different happens, that there is a decrease in the radius, that the atoms actually get smaller. So visualizing this on this blank periodic table, atoms get bigger as you go down a group. But atoms are bigger if you're considering left to right within a period. The biggest atoms are on the left side of the periodic table compared to the right side. So your largest atoms will be in the lower left part of the periodic table, and your smallest will be in the upper right hand part of the periodic table. The hard part of this is figuring out why. Why do we see these trends? Top to bottom within a group, this isn't too bad. Top to bottom within a group, you are adding one whole principal energy level into which electrons are placed. So essentially it's like you're adding, a layer to the onion, and the onion grows bigger and bigger. Okay, so you're adding a whole new principal energy level of electrons that get added as you go down each period on the periodic table. As you go down that group, makes the atom larger by adding layers. Left to right within the period, however, something different happens. In this case, electrons are being added as you go left to right, but they're being added to the same principal energy level. So you're not adding a layer, you're just putting electrons into the same layer. And if you can imagine what happens, that layer is going to get more and more negatively charged because you're adding more negative electrons into that same shell. But also as you're going left to right within the period, the charge on the nucleus is getting more and more positive. So the nucleus is getting more and more positive, and the layer is getting more and more negative. Well, positive and negatives attract each other, so what effectively happens is as you go left to right, the atom shrinks because the nucleus, the positive nucleus, attracts the increasingly negative layer of electrons, and it pulls it tighter, closer in, and the atom essentially shrinks. So the result is a greater magnitude of attraction between the increasingly more positive nucleus and the increasingly more negative valence shell. So we're going to conclude this video with a little video clip that will help you visualize this trend in atomic radius.
How can we explain trends in properties within the same column, as well as trends in properties across rows of the table? One observable trend is in atomic radius. There is no practical way to measure an atom's radius directly, but we can estimate the atomic radius by taking half the distance between the nuclei of two atoms. As we proceed down a group or family of elements, say from lithium to cesium, the number of electrons in an atom increases, and as you might expect, so do their atomic radii. But as we cross a period from left to right, the radii generally get smaller. One electron and one proton are added to each element. The nuclear charge dominates and the atom contracts. This general trend is followed for most of the S block and P block elements. But we see some small irregularities in this trend with elements in the D block. For example, going across the fourth period, we see a small decrease and then a small increase in atomic radius going across the D block. Why? Both the nuclear charge and the number of core electrons increase going left to right across rows in the D block. The increasing nuclear charge pulls the valence electrons closer to the nucleus, but the increasing number of core electrons pushes them away again. These two effects oppose each other. At first, the effect of increasing nuclear charge wins out, and there is a small decrease in atomic radius. But as more and more core electrons are added, the core electrons begin to win out.
This concludes the video lecture on periodic trends in atomic radius. There will be a second video describing the periodic trends in reactivity of metals and reactivity of nonmetals. That's it. Thanks for listening.